Thank you, students, for joining me in this latest installment of my Special Topics 3 lecture videos covering a systematic review of chapters 9 through 11 from General Chemistry. In today's video, we're going to begin by covering molecular geometry or shape. Are you ready? Let's go ahead and get started. Now, generally speaking, molecules adopt shapes that keep all of their atoms as far away or as spaced out from each other as possible. For example, in the molecule carbon tetrachloride, whose Lewis structure without all the lone pairs on the chlorines is shown here, the furthest apart that the 4 chlorine atoms can get on a flat two-dimensional surface like this screen is 90 degrees. However, in real life, we don't live in a two-dimensional world like this flat screen you're staring at. Molecules exist in a 3-dimensional world where each of these 4 chlorine atoms can actually spread out a little bit further than 90 degrees, like this. Okay, this might be a little bit difficult to see, but what this is trying to do is show you, three-dimensionally speaking, that in real life, carbon tetrachloride has its central carbon atom like this, and each of these chlorines is poking out a little bit further than 90 degrees because it's not flat. They're poking out three-dimensionally, as this model attempts to depict. The angle between each of these groups is 109.5 degrees. I'll show you that right now in a handheld model. So this is a cute little handheld model. Once again, you can see that this carbon atom, which is depicted as a black sphere, is surrounded by 4 individual chlorine atoms in this molecule of carbon tetrachloride, or CCl4. As I was just explaining, you can get in real life, in the 3-dimensional world, each of these chlorine atoms to be further apart from each other than 90 degrees, as would be the case if you were only in a 2-dimensional world. So this would be the overall shape that we would see in carbon tetrachloride. Now, this type of shape is called a tetrahedron. You can see that the chlorines, which are the green balls in this picture, can spread out from their central carbon atom to have about a 109.5 degree angle between each chlorine atom. So this idea, the idea that atoms spread out as far apart from each other as possible, is called the VSEPR, or valence shell electron pair repulsion model. Sometimes I just like to call it VESPR because it rolls off the tongue a little bit easier than VSEPR. Now, parenthetically, just so you know this, our book sometimes calls lone pair electrons non-bonding pairs or just lone pairs. Electrons that are shared between 2 bonding atoms, in our book at least, are called bonding pairs. The number of things, either lone pairs or other appendages around a central atom, is called the atom's number of electron domains. With that in mind, let's take a look at these different geometries from Chapter 9. As you can see, we've got a central atom bonded to 2 things, which means that it has 2 electron domains. Its electron domain geometry would be linear, and its predicted bond angle would be 180 degrees. By extension, you can pause the video and take a look at each of the predicted bond values and number of electron domains in each of these geometries, and I hope that you will. Here is an extended table showing a few actual real-life examples. In this case, I can have a linear example where I've got a central atom bonded to 2 other atoms, 180 degree bond angle between them, having 2 electron domains around that central carbon atom, and an example is CO2. In the case of a trigonal planar geometry, I can have examples where I've got 3 atoms, like these fluorines, around a central atom like boron, or I could have one of these groups be a set of lone pair electrons, as in this molecule, nitrogen dioxide. By extension, there are similar examples shown down here in the rest of the table. I invite you to pause the video and make sure you look at these and understand how to predict the number of electron domains, the number of lone pairs or non-bonding pairs, and the number of bonding pairs, as well as the bond angles for each of these examples and related examples by extension. With that in mind, then, let's take a look at some examples. The molecular geometry of the leftmost carbon atom, this one right here, in this molecule is what? Now, I'm not going to answer this question for you, but invite you to do it on your own. And now, another question. The molecular geometry of the rightmost carbon, this one right here, in this molecule is what? Once again, I'm not going to do it for you, but we'll let you do it on your own. That takes us to a new subject, that of orbital hybridization. Now, as you likely remember from previous discussions, to form desired bond angles, atoms often have to combine their orbitals to make new, previously non-existent orbitals. This process is called orbital hybridization. Now, to determine an atom's orbital hybridization, you have to count the number of things around that atom, and by things, I mean either another atom or a lone electron pair, and then memorize the following. If you have a central atom that has 2 things around it, its hybridization is sp. If you have a central atom that has 3 things around it, its hybridization is sp2. If you have a central atom that has 4 things around it, its hybridization is sp3. Let's take a look then at a lecture question. I want you to determine the hybridization and bond angle around each carbon and oxygen atom in the following molecule. Please note that I have not drawn lone pairs around this oxygen up top, so you will have to do that in order to get the correct answer. And here's another question. What is the hybridization of sulfur in SO2? Now, in order to answer this, you're going to have to draw the Lewis structure of SO2 and then determine how many things, either atoms or lone pairs, are around that sulfur atom. I'm not going to do that for you, but we'll invite you to do it on your own. Now to another subject, shape and polarity. So how do we determine if a molecule is polar or not? Okay, the way we do it is we follow these steps. First, draw the molecule's Lewis structure. Second, as best you can, redraw the Lewis structure to show the molecule's overall molecular geometry or shape. Third, draw arrows between every atom in the molecule going from the less electronegative atom, A, or whatever atom it happens to be, to the more electronegative atom, B, in each bond, like this. Lastly, you answer the truck question, which I'll now explain. Okay, that's sort of a lie. I'm not going to explain it here in this video, but I'll post a link here to a separate video in which I do. Let's take a look then at some example problems. I want you to predict whether each of the following molecules is polar or nonpolar. I'm not answering this for you here, but I will post a link to a separate video that you can use in order to help answer this question on your own if you like. Here's another one. Of the molecules below, only something is polar. Which one is it? I'll let you see if you can figure that out. And this question, of the molecules below, only something is nonpolar. Well, that seems like a good place to stop this video. Please stay tuned to the next one in which I'll begin reviewing the combined gas law. Until then, have an enjoyable rest of your day.